What happens if you eat uranium? If you have ever pondered the effects of eating something as dangerous and mysterious as uranium, you are not alone. The concept is both morbidly fascinating and scientifically complex, weaving together strands of chemistry, physics, medicine, and history. To fully explore what happens if you eat uranium, we must embark on a journey through the realms of toxicology, radiation, human anatomy, and even the laws governing the use and handling of this element. This exploration seeks to provide not just a simple answer, but a thorough understanding of the many ways uranium can impact the human body, and why, under no circumstance, should anyone intentionally ingest it. Let us begin by understanding what uranium actually is. Uranium is a heavy, silvery gray metal, naturally radioactive, and found in small amounts nearly everywhere in the environment, from rocks and soil to water and air. It is recognized most infamously as the critical material for nuclear power and weapons. Chemically, uranium's most common form is uranium oxide, but it can exist in several chemical forms, each with its own characteristics and degrees of solubility. For the purposes of considering what would happen were someone to eat uranium, it's important to realize that uranium naturally occurs most abundantly in the isotope uranium-238, with much smaller amounts of uranium-235 and traces of uranium-234. All forms are radioactive, though not equally so. Many people might assume that uranium is instantly deadly simply because it is radioactive. However, the full story is more nuanced, as the harm from uranium comes from two sources: its inherent chemical toxicity as a heavy metal, and its radioactivity. To address the first, let's consider heavy metal toxicity. Uranium, like other heavy metals such as lead or mercury, can be chemically toxic to the human body, especially to the kidneys. When uranium enters the body, whether by ingestion, inhalation, or injection, the body treats it in ways akin to other heavy metals. If you were to ingest uranium, the first thing to consider is how much is absorbed by your digestive system. Interestingly, the gastrointestinal tract is not very efficient at absorbing uranium. Only about 1 to 2% of ingested uranium actually enters the bloodstream. The remainder passes through the digestive system and, assuming it is not in a highly soluble form, leaves the body through the feces. But what about that small percentage that does get absorbed? Once uranium enters your bloodstream, it tends to accumulate in bones, kidneys, and to a lesser extent, other tissues. The kidneys, being highly vascular and tasked with filtering the blood, are particularly vulnerable. Similar to lead or cadmium poisoning, uranium can damage the kidney's filtering structures, leading to a form of nephrotoxicity. Acute exposure to high levels of uranium, levels much higher than any natural exposure, can lead to severe kidney damage, and in rare or extreme cases, kidney failure and death. Clinical studies have provided insights into the effects of uranium poisoning in humans. During the 20th century, particularly during and after World War II, experiments studied uranium exposure in various forms. These studies demonstrated that symptoms of acute ingestion, at doses likely far in excess of any accidental or environmental exposure, can include nausea, vomiting, diarrhea, abdominal pain, and kidney pain. Chronic exposure to lower doses can also cause reduced kidney function over time, though the human body is fairly good at eliminating uranium, provided the dose is not too large or repeated. To make the scenario more concrete, imagine someone eating a small piece of depleted uranium, not enriched reactor-grade material, but the less radioactive byproduct of the enrichment process. Their exposure to uranium's chemical toxicity would be less than from more soluble uranium compounds, but even so, the risk would be present. If the uranium were in a more soluble form, such as uranium hexafluoride or uranyl nitrate, it would dissolve more easily in the body, leading to greater absorption and higher toxic risks. The second, and intuitively frightening aspect of uranium exposure is its radioactivity. Uranium, as a radioactive element, decays slowly, releasing alpha particles in the process. Alpha particles are a type of radiation composed of 2 protons and 2 neutrons, the nuclei of helium atoms. They are highly ionizing, meaning they can break chemical bonds and damage biological molecules. But they cannot penetrate far. In fact, a piece of paper or the outer layer of human skin can stop alpha particles. This is why uranium, or materials that emit alpha radiation, are primarily dangerous when they are ingested or inhaled, rather than simply handled. So, if someone eats uranium, what happens at the atomic level? The uranium will emit alpha particles as it undergoes radioactive decay. Inside the body, alpha particles can directly interact with nearby cells, causing ionization. This can lead to damage to DNA and other vital cell components, which in turn can cause cell death or mutations. While the risk per atom is very high, alpha particles are extremely damaging at close range. The overall radioactivity of natural uranium is quite low compared to materials like radium or plutonium. A gram of natural uranium emits about 25,000 alpha particles per second, a mind-boggling number, but not enough to cause acute radiation sickness by itself. The more pressing issue for most exposure scenarios remains kidney toxicity. If, hypothetically, someone swallows a lump of uranium metal, what is the outlook? The metallic uranium is not highly soluble, so only a small fraction will be absorbed by the body. Most will pass through the digestive tract without being absorbed and be excreted in the feces. As it passes through the intestine, its radioactivity primarily comes into close contact with the tissues lining the digestive tract. Here, there is some localized risk of cell damage or mutagenesis, especially if it stays in the gut for an extended time or if the uranium is finely powdered, increasing the surface area for absorption and exposure. In rare cases, this could increase the risk of gastrointestinal cancers, though the overall risk from a one-time swallowing event is probably modest compared to the risk from repeated or occupational exposure. But what if the uranium was not metallic, but instead a soluble compound like uranyl acetate? In this case, a much larger fraction might be absorbed by the intestine, leading to greater systemic exposure. Acute poisoning can then produce symptoms within hours: nausea, vomiting, and, as previously described, signs of kidney damage. It is also important to address what doesn't happen. Contrary to Hollywood or comic book portrayals, ingesting uranium will not make you glow, nor will you gain superpowers. The real-life consequences are mundane but dangerous, involving chemical and radiological damage at the microscopic level rather than spectacular external effects. When considering possible accidents involving uranium, history provides some grim lessons. Uranium miners, millers, and workers in the nuclear industry have developed kidney problems, bone cancers, and increased rates of leukemia and other illnesses after years of exposure. Many of these risks come from inhaling uranium dust rather than ingesting it, but the risks upon swallowing soluble uranium compounds are not trivial. Suppose someone, perhaps a miner or a person in a region with high environmental uranium, is regularly exposed to small amounts of uranium in drinking water. What happens over years of such chronic, low-level exposure? Multiple studies have found that uranium concentrations in the urine, used as a proxy for exposure, can be correlated with decreased kidney function over time. Some studies have linked chronic uranium exposure to increased risks of cancers, though separating the effects of uranium from those of other contaminants can be challenging. When examining worst-case scenarios, like the hypothetical of eating a large amount, a few grams or more, of highly soluble or powdered uranium, the acute effects would be pronounced. There would be immediate toxicity, likely causing symptoms of gastroenteritis, followed by potentially rapid-onset kidney failure. Emergency medical intervention would be required, and depending on the dose and form, survival would not be assured. On a regulatory and safety front, uranium is a controlled substance. Mining, handling, and especially possessing uranium compounds in any notable quantity is strictly regulated. Part of this is to prevent environmental and workplace exposure, but much is also due to the security risk associated with uranium's role in nuclear technology. What about animal experimentation? Since human experimentation is unethical, science often relies on animal models to assess the risks of uranium. Laboratory studies have shown that animals exposed to uranium develop similar symptoms as humans, primarily kidney damage and, over long periods, increased cancer risk. These findings have been cross-validated in occupational epidemiology. For context, daily human intake of uranium in most locations is minuscule, fractions of a microgram per day from all sources combined. Human bodies have evolved to cope with trace amounts of uranium in the environment, so long as levels remain low. However, once exposure crosses into the higher microgram or milligram range, risks escalate sharply. What then is the management for someone who has accidentally ingested uranium? Medical treatment focuses primarily on preventing absorption and supporting the kidneys. Chelating agents, chemicals that can bind heavy metals and help remove them from the body, are sometimes used, though their effect is limited. Most cases rely on supportive care, hydration, careful monitoring of kidney function, and sometimes dialysis if renal failure ensues. For those with chronic exposure, the focus is on reducing ongoing intake, purifying water, reducing environmental accumulation, or changing occupational practices. In every instance, prevention is far more effective than treatment. It is also worth noting that not all uranium exposure leads to immediate illness. Many people working with uranium or living in areas with high natural concentrations develop no symptoms in their lives. This is due to a combination of dose, individual susceptibility, and the form of exposure. However, the risks are cumulative, and even if short-term symptoms do not develop, long-term health can be compromised. Why, then, has the dangers of uranium been such a focus of study and regulation? The answer lies in uranium's dual danger. Its radiological threat is not as immediately lethal as other radioactive materials, but its abundance and role in nuclear technology make it a unique risk. From the atomic age onward, accidents with uranium, and with the much more dangerous materials produced from it, like plutonium, have driven scientific, governmental, and public health efforts to understand and mitigate the risks. In conclusion, what really happens if you eat uranium? The outcome depends on the amount, the chemical form, and the duration of exposure. Ingesting a very small amount, such as a tiny trace from water or food, is not likely to cause immediate harm, though chronic exposure increases health risks, primarily to the kidneys. Eating a larger amount, especially of a highly soluble form, risks both acute chemical toxicity, affecting the kidneys, and long-term radiological harm. Most ingested uranium passes through the gut without being absorbed, but the small fraction that does enter the body can be stored, primarily in bones and kidneys, for years, continuing to expose tissues to alpha radiation and potentially causing harm over the long term. That is why handling uranium is strictly controlled around the world. It is why uranium is not, under any circumstances, to be treated as something safe to ingest or even to handle without proper precautions. The combined chemical and radiological risks are invisible, insidious, and dangerous, with decades of science and tragic history to prove their seriousness. To anyone curious, the best approach is to treat uranium, and indeed, all radioactive or heavy metal substances, with the utmost respect and caution. Human curiosity about the unknown is natural, but our knowledge of uranium tells us one thing for sure. What happens if you eat uranium is a story of the silent, invisible, and ultimately deadly power of nature's most potent elements.